So, hello everyone, welcome back. I hope you had a nice Thanksgiving break. So we will continue discussing about database systems, but now we are looking at different data types for a change in this and in the following lectures. So far, we have been mostly discussing about tabular relational data because that's a very common data format used in practice. But there's a couple of other data formats for which people have developed specific specialized systems, and we are going to discuss about some of them. In particular, we're going to discuss about graph data. Today, we are going to discuss about data streams, and we are going to discuss about spatial data and about systems that have been designed specifically for those types of data. Now, today we're going to start with graph data. And here is a reading list that connects to some of the things that we will discuss. So that is not necessarily covered by the course book anymore, but here you can find more details on the topics that we are about to discuss. So a graph is generally a collection of nodes and edges connecting those nodes. So often those nodes will represent things or persons, and those edges will represent relationships between them. Those nodes and edges can often be associated with labels. Often that corresponds to something like a node type or a relationship type. And additionally, you can often associate them with properties which give you additional information about the entities or about the relationships. This is a simple example graph over here. In blue, the circles are the nodes, and here with the column, I'm representing labels. So here we have two nodes labeled as students, then a course node and a university node. And in green, you have those additional properties for the nodes. So here we have two students, Mark and Maria, which are apparently enrolled in the CS4320 course. And on the right-hand side, we have the Cornell University node, which offers the CS4320 course. So it is a very simple example. You have nodes, edges, and properties and labels. Now, this is a little toy example, but in reality, we have nowadays a lot of data sets that are natural to represent as large graphs. If you think, for instance, of social networks, of a knowledge graphs like the Google knowledge graph, of communication graphs, of road networks, and so on and so forth, in many cases, it is quite natural to think of that data as a graph. Here, for instance, we have a representation of a communication graph here. Nodes represent servers on the internet, and the edges represent connections between them. Or here we have a representation of the Facebook graph. So here nodes correspond to people, to profiles, and edges correspond to connections between those profiles, and you can represent it as you see here. Or here, slightly less mesmerizing, but very practical, we have a graph representing the NYC metro network. So in this case, we would have nodes representing metro stations here in Manhattan primarily, and the edges correspond to direct connections between those metro stations. So now I have marked up two locations on that map that I will use as an example here. We've marked up the Port Authority bus terminal. This is what we would arrive to when coming by bus from Ithaca, for instance. And here I have marked up also NYU, New York University. And maybe at some point when things open up again, then I might want to visit a colleague there at NYU, and then I might want to find out how many paths connect the bus terminal to the metro station at NYU. And in the following, first of all, let's think about how we could solve this problem, like showing all the possible connections with a relational database. The first thing we need to do in order to use a relational database is that we represent that graph as a relational database. Does anyone have a suggestion about how we could represent this graph, or perhaps graphs in general, inside of a relational database system? Yes, very good. Yes, very good. So here, yes, yes, very good. Okay, so thanks, that is correct. So here I have multiple correct versions. So we probably want to introduce a table to store the nodes and another table to store the edges, which has perhaps some foreign key references to the nodes. So in this case, that could be one table with stations. Here the station ID is the primary key, and then each station has a name. And then a table connected, so those are the edges. This table references two nodes from the stations table via foreign key references, and the primary keys, then the combination of the two connected stations. So in this way, I could represent this graph relatively conveniently in a relational database. Now, what I want to do is to find all possible connections between those two specific nodes in my graph, having stored the data in my relational database system. Can anyone suggest a query by which I can calculate those connections using the SQL features that we have seen so far? I have this table with the stations. I have this table with the connections between stations. Maybe if you think about how you can find paths of a specific length, for instance. In the end, we are interested in paths between two specific nodes. So we somehow might have to combine multiple rows from the connections table. Now, if I, for instance, want to find out from one specific node which are the other nodes that I can directly reach in one step, then I have that information directly in the connections table. Now, if I want to expand that and find out all the nodes that I could reach in 2 steps from some initial node, any suggestions about how we could proceed? Okay, very good. All right, here that is the, yes, that is correct. And here the perfect keyword in there, that is a self-join. That's what I probably want to do. So I need to use the connections table multiple times because it will be searching for paths that have multiple steps to them. So this query here gives you the template. So I have those self-joins between the connected table, where I'm always making sure that I connect the second station in the last instance of the connected table to the first of the 2 stations in the next instance of the connected table. So this whole thing forms essentially a chain of joined tables. And then finally, I just have to make sure that I'm starting from the port authority node by putting the corresponding restriction into the where clause. And the final node that I want is NYU. I can also put that as restriction into the where clause. So, and if I join this connection table, connected table, a fixed number of times, then I get paths of a fixed length, and maybe initially I don't know how long the path can be, so I could just iterate and take the union over a disk query with a different number of connected tables, right? So this is what I could do. Is there any questions about that representation here? All right. So as you see, okay, very good. So if you really want to use a relational database system, in this case, then yes, we could use something like a loop with a stored procedure or with some surrounding software which issues multiple queries. There's also a couple of more advanced SQL features which would resolve this more elegantly. But this is mostly to show to you that maybe using traditional relational interface, using the SQL features that we have seen so far in this scenario might not be the most elegant way to go about it, right? Because here already I have they have a lot of joins here that I would have to symbolize, and I might have to repeat that with a different number of joins in order to get paths of a different length. So it's not ideal, let's say. So the intermediate conclusion here is that we can generally represent graphs in a relational database management system. But using the SQL commands that we have seen so far, it's not exactly convenient to ask queries like the one that I have shown before. And that means that there's potential for specialized query interfaces that are targeted at graph data. And also, we will probably discuss about that more in the following lecture. Perhaps there's a couple of ways in which I can change the design of my system in order to make it more efficient to process graphs in particular. So there's a couple of motivations why we might want to look at systems that are specialized to graph data. And there have been quite a few systems proposed. Here you see logos of some of those systems, but that's only a subset. Now, those systems use a slightly different query languages, and they have slightly different functionalities, but all of them are targeted at graph data. And in the following, we're going to look at one of those systems in more detail. That is the Neo4j system. It's one of the most popular systems, but that's not to say that those other systems aren't great as well. So this Neo4j system, first of all, has a specialized query language specifically for graphs. And in the following, we're going to discuss more about that language. So the name of this language is Cypher. And this language allows you to do things such as creating or updating nodes and relations in your graph, to search for specific patterns in your graph, doing things like aggregation, filtering, that supports subqueries, and so on. So in many ways, this language is somewhat inspired by SQL. You will see some common points, but it is specialized to graph data. So in the following, I'm gonna show you a couple of examples for how you can use this language. Later, we will also see a little demo with the Neo4j system. So the first thing that you probably want to do when working with that system is that you want to create a graph that you can work with. And here you see some commands for creating nodes in that graph. So in the most simple version, you can create one anonymous node with a create command, and nodes are always represented between those round parentheses here. So the first command here just creates an anonymous node without any labels or properties. The second command here specifically creates a node labeled as a student. That's always marked with this a colon symbol followed by the label, and that typically represents something like the node type. The final version is more expressive and additionally adds a property to the node, which we have between those special brackets. And here we essentially attach the property name with the value mark to this student. So that creates a node probably representing a student called Mark. Now, in the following, I'm going to show you how we can add edges, relationships to your graph. Before we can do that, we have to learn how to identify specific nodes in our graph so that we can tell the system between which nodes we want to add an edge. So if you are searching for a specific node, you can do it, for instance, with the command that you see here. Here, I'm asking the system to match nodes of label student and having a property name with value mark. And I'm asking the system to match such nodes to the variable m. So m is what you have here before the colon symbol. And if we use the match command, we ask the system to match this pattern here to the variable m, and then I can use variable m in the remainder of the query. So here, for instance, I want to create a relationship, an edge between the student node Mark and the CS4320 course node. So what I do here is, first of all, I match variable a to a node of label student with property name set to Mark, and variable b to a node of label course with name property set to CS4320. And then following that, we have the create command. So here we create a relationship between those two nodes. We have a, the variable from before, and b, the other variable from before. And now I'm creating a directed edge from a to b. So this notation is relatively intuitive. You see that the edge is represented by essentially a little arrow in ASCII representation. Also, we have given a label to that edge, which you have between the square brackets. Those edges can also have labels. Here, we label the edge as enrolled, and the semester property is set to fall semester 20. So this matches the two nodes that I want to connect, and then it creates indeed a connection between those nodes. If you have any questions about this, then please don't hesitate to ask them in the chat. All right. If you have created nodes, then you can also change them later. Of course, you can update nodes. So for instance, here, first of all, you're telling the system which are the nodes that we want to update. Here, I want to update the node labeled as student with name property set to Mark again. And here I can, for instance, change the label of that node. Perhaps a student finished the studies, and then I can set the label to alumnus rather than a student. That's what the first command is doing here. Also, maybe there was a name change, or I got the name wrong the first time, so I might want to adapt the name property. So the second command searches again for that same student and now sets the name property, which you write with the variable name dot and then the name of the property. And here we set that to Marcus instead of Mark. So I can also update relationships before we can update the relationships, we first have to find the corresponding relationships. Okay, and here's some interesting questions. So you can batch updates to nodes. In any case, if you write a matching expression, then the update will refer to all nodes that satisfy this matching expression, right? And generally, nodes can have multiple labels, but if we reset the label, then it will override the old labels. Okay, very good. So the difference between a label and a property is the question. So a property always gives you essentially, it has two types of information. I mean, you have the name of the property, and then you have the associated value of the property. A label consists only of the label name, basically. So the way it is typically used is that the label indicates something like a type of a node, and the property gives you some additional information. So here, for instance, in order to express that some node represents a student, it is natural to use a label because we don't need any additional information beyond that. But in order to assign a student to a specific name, we probably want to use a property, as we can also assign a value in this case. So yeah, typically labels used for expressing types and properties used for expressing additional information about a node or about a relationship. And if we reset the label, we will not delete the existing properties. Great questions. All right, good. So please feel free to add more questions in the chat here. All right, so the next thing that I will discuss here is how we can update relationships and edges. And the first thing we need to do is to find the relationships that we are interested in. And I can also do this with the match expressions. So here I'm searching for relationships that connect this node of type student with a name property equal to mark to a node of type course with name property CS4320. And I want them to be connected by a relationship of type enrolled with the semester property set to fall semester 20. So we are talking about the current semester. As you see, I can also assign a variable to one of those edges, here E, and then I can use that variable to refer to it later. So here in this matching expression, I'm asking the system to assign 3 variables for me. The first representing student mark, the second representing course CS4320, and the third one representing the connection of type enrollment between the student and the course. All right. And now in the following, I'm going to use this matching pattern to find those edges. And now I can, for instance, update the semester because now time has passed perhaps. So I can update the semester to fall semester 21 instead, for instance. And I'm also going to do this with the set command. I think there's one more question in the chat. All right. How does Cypher deal with nodes with the same properties if there is 2 students named Mark? That is totally possible. And with the syntax that I have shown you so far, it would essentially mean that a variable is assigned to a list of possible matches. And if you do something with those matches, if you, for instance, update them, or if you delete them, or if you just want to show them, then that would happen to all matches. So if there's multiple students with the same name, then you would match all of them. Okay, and here a very, very good question. The question is about the nature of the relationships, because indeed we have seen a slightly different syntax, very good observation. So in a graph, you typically have directed and undirected edges. So in Neo4j, the database needs to contain directed edges between nodes. So if you have, for instance, created the relationship here, as you see here, we have made a little arrow between node A and node B. So here at the end of the command, on the right-hand side of the line, you see this arrow representation. So this is specifically an edge that points from node A to node B. Now, on the other side, when we were searching for edges, and that's a very good observation, here we didn't use any arrow in this expression. And that essentially means that here we are not making any restrictions as to in which direction the two nodes are connected. We could do this if we want to, but here in this case, we probably only have connections in one direction. So this representation, this notation without the final arrow tip, it means that we are looking for connections into both directions. Good observation. Yes. But if you're creating edges, then you always have to indicate the specific direction. If you're searching for relationships, then you can leave out the direction, and then you will find connections in both directions. But when creating them, you have to say which direction it should be. Good. All right. So here, the last thing that we have seen is how we can update a relationship. We can also delete things, of course. So here, for instance, we're asking the system to match variable A to all students in the database with name Mark. So that could be multiple students indeed. And for each student matching this expression, I want to delete the student, right? And I can do so in a similar way for edges. Now, in order to make this more concrete, I'm going to show you a little demo for how using the system looks in reality. Let me quickly share the other window. Okay, and here one more question, whether it's possible to only match a node using an edge but not specifying the property. Yes, absolutely. You don't have to specify any properties during the matching. You can just match nodes based on their connections, for instance. So yes, having properties in the matching expression, that is optional. All right. Good. So here I'm on the website, and if you want to try that with the examples that we have in the slides, then you would go to get started here. There's an online sandbox that we can use here, so you don't necessarily have to install anything. And here we have, for instance, a blank sandbox, which allows us to play starting from an empty data set. Now it's loading the interface. All right. And here we are. So now we can enter those commands that we have seen before into this little query box over here. So perhaps let's first of all create a couple of nodes. Here, this is the simplest version of it, which creates just one anonymous node without label and without properties. Right, and here I'm getting some feedback. It has succeeded. Now let's maybe replicate some of the examples that we have seen. So here we are creating a student called Mark, for instance. Right, now I've created that. And perhaps another student, we are, and now I can create a course, for instance. So I'm pretty much following the example that we had in the slides to see how that works when actually entering it. Right, and now perhaps I want to create a relationship between the student and between the course. So we first have to match that. I ask the system to match students. Let's actually say all the students to variable s. And here I'm matching to variable c nodes of type course with name equal to CS4320, which would not be necessary here because we don't have any other courses in the database currently. Now we are enrolling everyone into CS4320. Right. Okay, and here you have a little warning. Right, that is fine. Right, and now here we have created two relationships which has essentially assigned both of the students to the corresponding course. And we're going to see a little bit more commands in the following, but here you see a little bit how the interface would work. And now perhaps let's clean up again, and we can delete the students again. And we had before the question, what happens if my matching expression matches multiple elements in the database? That is the case here, for instance, because I'm not fixing the name. We also had the question about whether we need to fix properties in the matching expression, but we don't need to do that. And here I'm simply matching all students, all nodes labeled as student in the database to the variable s, and I'm going through them and delete them. Now, if I execute this command here, it actually will not work because those students are currently in a relationship. And if I want to delete the nodes, I would have to delete the relationship first. So this should not work. If I try it, I get this error over here. So the first thing I would need to do here is to delete the corresponding relationships. So here maybe I'm matching relationship E to connections between students and courses. And now I'm deleting those relationships here. Right, and now I have deleted those two relationships which correspond to connections for the two students to the one course in the database. And after I have done this, now I can rerun the previous command because now I shouldn't have any relationships anymore between the students. All right, now I have deleted those two students again. Yes, so this is a simple example. Towards the end of the current slide deck, we will have another quick look at a more interesting example, but I already wanted to show you a little bit how to use this interface. All right. All right. So now that we have seen a little bit how to create simple graphs as a little exercise, I wanted to ask you to create a graph representing the following situation. Here, we have a couple of different types of nodes. Let's say that we have Ithaca and Binghamton, which are cities which are located in New York. Cornell University is located in Ithaca, and it offers a course with name CS4320. So I give you just a little bit of time to think about how you would represent this as a graph and create the graph in the database system. You can do it on paper, or you can try with this interface that I have just shown. And while you're doing that, I'm happy to answer any other questions that might pop up. I'm gonna give you 1-2 minutes, and then we're gonna see a few more commands. No questions currently. That's a good question, but it's poor style to not be as specific as possible when matching. Frankly, I would say if you are not specific enough during matching, then there's a risk that you might match some nodes that you did not expect. So as a tendency, I would recommend to be as specific as possible in matching. Yeah, I think it's good practice. Yeah. Okay, and the website, if you just Google for Neo4j, the name of the system, then you will find it as first match. Yeah, so I would recommend to be as specific as possible in the matching. Of course, there's some limit. I mean, at some point you might have a database which has lots of properties for the same node, and then you might not want to specify all of them. So yeah, but in case of doubt, I would recommend to be more specific. All right. Okay, let's quickly solve this little example. All right, so here we asked about creating nodes to represent the cities, Binghamton and Ithaca, and those cities should be located in New York State. Let's perhaps first of all create a node which represents the state. And by the way, I'm gonna do it in one way, but different possibilities would be valid here. So let's create this node. And here, let's create this node, for instance, and Binghamton. And now we are connecting those city nodes to New York State. And admittedly not very specific in this matching expression. Actually, so here we're going to match city nodes to state nodes. And here we're going to add an edge that's pointing from the city to the state, and we can label it as located in. Okay. Right now we have created those relationships, and we also wanted to represent Cornell University. So let's create a university node with a name, Cornell, and just making sure I'm typically using the property name, but you could use a very different properties as well. Let's maybe just call this university name to show that properties can have different names. Okay, and actually I want to create that node. Right, and now I'm adding connections between Cornell let's be specific and add the university name here. We assign it to variable u, and we assign the city Ithaca to variable c here. And here we are creating the connection between u and the city C. Okay, right. And now we still wanted to introduce a course node. So let's do that. We creating the course, and now finally we are creating the connection. Or maybe other way around. Here we're creating the connection between the university, which in this case, there's only one university in my database, but I might want to specify the name anyway. Now here we are creating offers relationship in order to express that the university offers this course. Okay. All right. And duplicates of the same node. So there's a question about how we prevent duplicates of the same node. So it depends on what you mean by duplicates. I mean, every node that gets created here gets assigned some unique ID, but you might, for instance, have two nodes that are both labeled as students and both have the same name properties, for instance. That might happen. You might have, so basically, yeah, if you detect any duplicates, then you could delete them by referring to the ID. So yes, typically you would not want this kind of duplicate, and then you could delete one of them. There's a question about how we visualize relationships that we created. So I wanted to show more search queries next time, where we visualize the outcome, but let me maybe make one quick example here. So for instance, we have the relationship between the cities and the state. So here, for instance, I'm searching for all connections between city and state, maybe of type located in, and then I could return all of that, and the representation that it would give me here would indeed take the form of a little graph here. Okay, so here we have the different nodes represented in this mini graph. Over here, we have Binghamton and Ithaca both pointing to New York. We can shift that around a little bit, and here maybe make sure that we can see the labels of those edges. So this gives you also a graph representation of your query results. And the edges here, so there's a question about whether the direction of the edges has any significance here. So in general, you need to decide on a direction for the edges, and then it is a matter of a preference, whether you, for instance, whether want to represent an edge going from the university to the course with the label offers, or an edge from the course to the university with a label offered by. So there is some room for preferences, what you find most natural as a representation. You have to choose a direction when creating it in the database, but when querying, for instance, in the matching here, I haven't specified any direction, so this is why I didn't have any arrowhead in my queries. All right, so that was a little example as an intro to how to create graphs in a graph database. The next time we're gonna look into how we can query those graphs, and we're gonna look a little bit behind the scenes of how those graph queries are processed internally. I see you again. We're at the end of the time, so I see you again on Wednesday. Have a nice day.